Hi, Nick Pizzi here, and this is the last video in the series, the three-part series that we're putting together for distribution system operators, helping them to prepare for exams. I'm going to share this screen with you, and we'll get through with those last set of slides. Hopefully you've had a chance to see part 1 and part 2. So we're going to pick up with question number 15 on part 3. As you may recall, the first 2 sessions that we did depended on some sheets of schematics, some data, operating data, and also some design data. These last remaining questions do not depend on those sheets. So these are standalone questions, but they are ones that are typical of distribution system exams, especially some advanced ones. So let's work through those now. Remember, as we go through these, you can always halt the video or pause it and work on some of the problems and get back to the video to see if you got it correct. So the first one asks this, and this is a standard question on all the exams. How many 4-inch diameter pipes do you need to equal the capacity of an 8-inch diameter pipe? This is something that they ask a lot, and they're trying to get us to think about certain things here. So here's the way I attacked this problem. I took the 8 inches and turned it into feet by dividing by 12 inches. So 8 divided by 12 is going to be 0.66 feet. And then I figured out the area of an 8-inch pipe. It's going to be 0.785 times 0.66 times 0.66. In other words, the diameter squared. I come up with 0.34 square feet. And so what we're trying to determine here is this. How many 4-inch pipe areas does it take to equal that 0.34 square feet, which is the area of the 8-inch pipe? So let's work that out. An area of one 4-inch pipe will be 0.785 times 0.33 times 0.33, or 0.085 square feet. So then if I take the 0.34 square feet of the 8-inch pipe and divide it by the square foot area of one 4-inch pipe, I see that I need four pipes to do that. A lot of people would think it would only take 2. Why does it take 4? And that's the point they're trying to get you to think about. This type of question comes up on exams because they're trying to get you to understand when you double the diameter of a pipe, when you go from a 3 to a 6, or a 4 to an 8, or an 8 to a 16, you quadruple the space involved because you take the diameter and you square it. So 2 squared is 4. So it's 4 times the volume than it is the diameter. So think about that. It's always a question that comes up. Okay, let's move on to question number 16. This is a velocity question. Calculate the velocity in a 24-inch main if the flow through it, let me move my video out of the way from my site, if the flow through it is 875 gallons per minute. This is a V equal Q divided by A question. And if you want to work this, go ahead and pause the video now and give it a shot. All right, you're back. Take a look at this. Looking for the velocity in a 24-inch main if the flow going through it is 875 gallons per minute. So when you calculate velocities using this formula, it's always important to get the numerator and the denominator into agreement as far as units are concerned. You can't deal in gallons per minute and cubic feet in the same formula. You've got to get them the same. So flow is typically going to be given to you in the problem as either gallons per minute or cubic feet per second. So whatever units you choose to work with, you may have to convert something else to those units. So if the area is in square feet, we may need to convert this. So here's what I did. I took the 875 gallons per minute and I divided it by the square foot area by taking 3 pi or 3.14 times 1 times 1. And so 875 gallons per minute times 1 cubic foot per 7.48 gallons divided by the 3.14 square feet is going to give us a velocity of 37.25 feet per minute. So 37.25 feet per minute divided by the 60 seconds per minute will give you 0.62 feet per second, which makes sense for such a small flow in a 24-inch main. So hopefully you found that one and got it through okay. And we'll move on to question number 17. Now 17 addresses the issue of repairing and disinfecting broken mains in the system or repaired mains in the system, which then requires you to flush it out at 2.5 feet per second and spend exactly so much water to get it done properly. So this question asks you, how many gallons per minute must you use to flush that main out? And the second part of it is, how long should that take you? So in other words, you've got this 1,000 feet of 6-inch main that you've repaired, and you decided to flush it out after you got it disinfected. AWWA and probably your state requires you to flush it at 2.5 feet per second in order to get a high enough velocity to get the water out of there. Well, if you can't measure that 2.5 feet per second, you're going to have to do some calculations. And so you're going to need to know how long it takes to flush. Probably you're going to use a pedometer in the field to figure things out for yourself. So here's how I work it. First, I'm going to calculate the gallons per minute that's needed to achieve a 2.5 foot per second velocity in that 6-inch main. No matter how long it is at this point, technically you should be under 1,200 feet because you don't want to get friction involved in this. But when I'm under 1,200, I'm going to use this 2.5 foot per second velocity. 6-inch main, I'm going to do it this way. The flow rate equals the area times the velocity, or 0.785 times 5.5 times 0.5, or the diameter squared, times the 2.5 foot per second velocity. That's going to equal 0.49 cubic feet per second. I'm going to want to change that to gallons per minute. So I'm going to take the 0.49 cubic feet per second, multiplied by the fact that there are 60 seconds in a minute, and then multiply by the fact that there are 7.48 gallons in every cubic foot. When I work that through, I come out to 220 gallons per minute. All right, so now I know at what flow rate I should flush the main, 220 gallons per minute. How long should I take to do this in the field? While I'm flushing at 220 gallons per minute, I know I'm at the right 2.5 feet per second, but how long should I keep that up to get the 3 volumes out of there? First, calculate the 3 volumes of 1,000 feet of 6-inch pipe. The volume is going to be, I'm going to put 3 times 0.785 times the 5 feet, 0.5 feet squared times 1,000 feet of it, and multiply that by 7.48 to convert those cubic feet to gallons. And I come up with the volume of 3 volumes of a pipe of being 4,403 gallons. So now it's just a simple matter of taking that volume and dividing it by the number of gallons needed by the flow rate. For 4,403 gallons, multiplied by 1 minute over 220 gallons, that's the flow rate, I come up with 20 minutes. So the problem then is solved. I should flush at 220 gallons per minute to achieve the 2.5 foot per second velocity, and I should keep that up for 20 minutes to get 3 volumes of water out of the pipe. Okay, hope you did well on that. Let's move to question number 18. This is something you get when you get a customer complaint about wastage of water. They think their water bill is too high. So you're investigating this customer complaint in which a larger than normal water bill is being disputed. You know, if you get a customer that complains about their water bill, and you notice a utility sink or something that's leaking, if you can determine that the leak is substantial enough to have made a high water bill, you want to make an impression on that person. You want to just tell them, look, you've got a drip going there. That's why your water bill's high. They need to hear big numbers to prove things. And here's what I suggest you do. You get out your 1 gallon container, a plastic bottle or something like that, and you hold it under the drip for a certain amount of time. And you see that it took 1 minute and 38 seconds to fill up that 1 gallon container. How much wastage does that leaky faucet produce in April? See, I'm going to multiply it by 30 days of April. So I'm going to show them every month, this is how much water you're wasting here. This is why you're paying such a high water bill. And here's how I do this. I convert the 1 minute and 38 seconds to a decimal equivalent first. I'm going to take the 1, set it aside. I'm going to take the 38 seconds and divide it by 60 seconds. I'll come up with 0.63 minutes. So the total time that I held the jug under the leak was 1.63 minutes. And during that 1.63 minutes, excuse me while this thing freezes up on me, that's not a good thing. Okay, there we go. If I take the gallon per minute flow rate divided, make it the volume divided by the time, I'll come up with 1 gallon divided by 1.63 minutes. I was filling that 1 gallon container up at a rate of 0.613 gallons per every minute. So now I've got some ammunition I can work with. I'm going to take that 0.613 gallons per minute, change it into minutes per day, which is 1,440, change it to days. Then I'm going to multiply it by a 30-day month. I'm going to get the days to cancel out on me. I'm going to get the minutes to cancel out. It's going to leave me in gallons per month, which I can now show them is going to be 26,481.6 gallons lost during a month. Now that should make an impression on the customer rather than just telling them, oh, you've got a drip of 1 gallon. You know, taking you a minute to fill up a jug of 1 gallon. That doesn't really make much of an impression, but 26,481 gallons in a month does. And that will tell them that's why their water bill is so big. All right, let's move on to question number 19. Question number 19 is something that happens to most of us in the distribution system. We get called in to take a sample to determine the chlorine residual in the area. Well, when we go out, we find in this remote area that the only place available for us to grab a sample is a single family residence. You go down into the basement, you see that there's a meter there near the basement wall, and the wall is on the street side, so that's good. So that's where the water is first coming into the building, into the house. And there happens to be a sink right there down in the basement, so that's good. So we can flush that out, or flush the line, because we want to get the water from the main to come into our water bottle to sample. We don't want to just turn on the faucet and grab a sample of the water that's been standing in the service line for who knows how many hours. We're going to flush that, but we don't want to sit there flushing it all day, make the customer nervous about paying too much for their water bill. They're wasting their water. But we want to flush it long enough and be able to tell them, I'm just going to flush it long enough to clear the main so that I can get the water from the main up to the house. How long is it going to take to flush a 3/4 inch service line at a 1/2 gallon per minute, which is what they suggest you flush at, if it's 30 feet long? Here's how I did this. I'm going to convert the pipe diameter to feet. 3/4 inch is 0.75 inches. And if you divide the 7.75 inches by 12, you'll get 0.0625 feet. That's what the copper service line is. So the flush time then would be 0.785 times the volume quantity, which is 0.0625 feet times 0.0625 feet times 30 feet length, and then converting it to gallons by multiplying by 7.48. I'm going to divide all of that by the flow rate of a 1/2 gallon per minute. My feet are going to cancel out with the cubic feet, and the gallons are going to cancel out, leaving me in minutes. And I come up with a flush time of 0.688 divided by half a gallon per minute, 1.37 minutes, or 1 minute and 22 seconds. So a minute and a half, say, I flush the line out at a reasonable flush rate, and I'm pretty sure that I'm going to get water coming up from the main. Okay, let's move on to question 20, which is not really a question. It's something that I'm going to show you first to prepare for you for the question number 21. So this is some information about electrical use on motors and pumps. This is a horsepower problem. So I'm going to use some graphics to explain water horsepower, brake horsepower, and motor horsepower. So when I have a pumping system, I'm going to put electrical energy into my pump and run it. And that energy is going to be called motor horsepower. It's going to be put into that system, but not all of that work, or not all of that energy that I put into that motor is going to be usable. Some of it is lost as heat and inefficient. When you put your hand on an electrical motor that's running, you're going to feel some heat, and that's wasted energy. That is not going into running that pump. Horsepower is lost here because of the conversion of electrical energy to mechanical energy and other motor inefficiencies. So now the energy that comes out of that pipe is only a fraction of, pretty good fraction, but only a fraction of the motor horsepower put in. Coming out, then it's going to become brake horsepower. It's going to be fed into the pump, and now the pump itself is going to be inefficient. So some of that horsepower going into the pump, which has already been diminished, coming out of the motor, is now going to be diminished further. It's going to become water horsepower. This is horsepower lost at the pump because of slippage and friction and whatever. So as an example, sorry about that. As an example, if I put 12 horsepower supplied to that motor, that much electrical energy being put in, and what is the brake horsepower and water horsepower if the motor is 90% efficient, the pump is 85% efficient? So what they're saying is, if you put 12 horsepower into this system, only 90% of it is going to come out of the motor, and only 85% of that is going to come out of the pump. What are those values? So you take that 12 horsepower and take 90% of it, and that's going to be 10.8 brake horsepower. So I've gone from 12 horsepower down to 10.8 horsepower being fed into the pump. Now I'm going to lose even more. But I'm not losing of the original 12. I'm losing from the 10.8. So we got to keep that straight in our heads. Now I'm taking 85% of the 10.8, and that's going to come out to 9.2 water horsepower. Hopefully that was somewhat clear to you, and you'll be able to use it to solve this next problem. So let's go on to question 21. Question 21 says this: it takes 28 horsepower for a particular pumping application. Think of you got a pump, you got a motor that drives it, pour water out in the system, 28 horsepower is being developed. If the pump efficiency is 75% and the motor efficiency is 85%, what horsepower must be being supplied to the motor? So this is just the opposite of what we just did on the previous slide. There, we put a lot of horsepower coming in, We took some of it down to get out of the motor, and then took some of it down to get out of the pump. Now I'm telling you what the ending horsepower is. I want you to work backwards. Here's how I work this. They're asking for motor horsepower. So I'm going to take the brake horsepower is going to equal the water horsepower divided by the pump efficiency. I'm going to take the 28 divided by 0.75, and I'm going to come up with 37.8 horsepower. That's what the motor put into the pump. I'm going to take that and divide that by that efficiency, 0.85 or 85%. And I'm going to come up with 43.9 horsepower being put into the motor. Oops, went too fast. You can see that it took 43.9 horsepower being put in by me in order to end up with the 28 horsepower at the end, because I've lost from two inefficiencies there. Hopefully that's going to make all your horsepower problems go away in your mind. I know they're tough. Question number 22. Well, this is a good one. You're in the field at the site of a newly installed heavily chlorinated water main. You're using the drop dilution method to determine chlorine residual after the main has been sitting for the required 24 hours. So you take 10 milliliters of deionized water in your test vial, you dissolve the DPD reagent in it, you start putting drops of the heavily chlorinated water one by one into your vial. Then you see a color change. You decide to take a reading of it, and you get a 0.6 milligrams per liter chlorine residual after 3 drops. What is the residual in the main? You can assume that each drop of water is 0.05 milliliters. I think I have something coming over. This drop dilution method is used in the field when you're expecting to find a huge chlorine residual, like after you've heavily chlorinated a repair on a main. Normally, you would go out and take a sample of the system. You'd have your kit with you. You're expecting to find 1 or maybe 2 milligrams per liter chlorine, something small. You just take a water sample, you dissolve the powder pillow in it, and take a residual. Very simple. But you can't do that when you're expecting huge amounts of chlorine in the water. And the kind that you've used to disinfect the water main is going to be so big, it's just going to inundate that small system that you have. So typically, if you ran that back to the lab, a water sample, they'd be sitting there with their fancy glassware, expensive glassware even, that you don't want to bring into the field. And you'd be making dilutions of it to get a chlorine residual. You dilute it to 1/100th and then 1/10 or something like that. It takes very expensive, very accurate glassware, which you don't want to carry on your truck. Probably don't anyway. So you have to use something in reverse. You've got to use the drop dilution method. Instead of adding a chlorine powder pillow to your sample of water, you're going to take DI water and add the chlorine powder pillow, and then put just drops of the heavily chlorinated water into it, and use a comparison method to figure out your residual. And here's how it works. If I take 0.6 milligrams per liter, which is the reading that I got, multiplied by the 10 milliliter sample that I have, and divided by the number of drops that I used, which is multiplied by the amount of volume per drop, in this case 0.05 milliliters, I come up with the 40 milligrams per liter. So that's how the drop dilution method works, and that's what they typically use in the system when they're expecting heavily chlorinated water. Okay, so that is the end of part 3, practical math exam for distribution system operators. Hopefully that was of some use to you. If you did not see part 1 and part 2 yet, you're going to see some links scroll up here shortly. You'll be able to click on those, and that'll bring you to the first videos of this series. I suggest you go through those and work those out. And that's the end of our series here. Distribution exam for operators. Be sure to look for part 1 and part 2. Thank you for paying attention. I hope you do well on your exams. Good luck. I'm going to stop there.